Again, welcome to Jnana Learning, continuing with the lecture on transistor, and here we are discussing the characteristics of common base configuration. So actually, the performance of a transistor, that is when connected in a particular circuit, it can be determined from their characteristics curve, which relate the DC current and voltage of that particular transistor. And we have two characteristics, that is input characteristics and output characteristics, and these two characteristics are commonly called as static characteristic curve. So here we are determining the input characteristics and output characteristics of a common base configuration. So here shown the circuit arrangement for obtaining the input and output characteristics curve in common base configuration. So both the input and output characteristics can be determined from this same circuit arrangement. So as it is a common base configuration, we have already discussed the common base configuration, that is base is common for both the input and output, and here voltmeters are connected in order to obtain the voltage values, and the ammeters are connected for obtaining the DC current values, and here the biasing and are given. The markings, that is IE, IB and IC, are the emitter current, base current and collector current. VEB, that is the emitter base voltage. VCB, it is a collector base voltage. Then VEE and VCC are the bias voltages. So here it is shown for a NPN transistor. So this is a circuit arrangement for obtaining the characteristics curve, that is input characteristics curve and output characteristics curve in common base configuration. So here is the input characteristics for common base configuration. So input characteristics curve, it is the curve drawn between the emitter base voltage VEB and emitter current IE, keeping the collector base voltage constant or for a given value of collector base voltage. So here shown the emitter base voltage in volts, and here is the emitter current in milliampere, and here shown the curve for various values of collector base voltage. So in order to determine this input characteristics, first we keep the collector base voltage at a particular value, then by slightly changing the emitter base voltage we can find out the values for emitter current, and we mark that particular points and then plot the curve. Now from this curve it is clear that for a particular value of collector base voltage, this curve resembles the curve for a forward bias PN junction diode. Why? Because the emitter base junction is always in forward bias condition. So that's why the curve resembles the forward bias PN junction diode curve. Now from the input characteristics we can find out the input resistance for the transistor, that is the input resistance of the transistor, it is given as the reciprocal of slope of its input characteristics, and mathematically we can explain it as the input resistance which is equal to the change in emitter base voltage VEB. Actually we have to take the small value, that is a VEB, delta VEB divided by the emitter current, that is emitter base voltage, input voltage to emitter current, that is a delta values we have to take. And one thing that we have to note is that keeping the collector base voltage constant, that is for a constant value of collector base voltage VEB by IE gives the input resistance. Now this input resistance, this particular value, the input resistance will be quite low. Why? Because we know that for a small change in emitter base voltage, the change in emitter current is large. Okay, that is from the curve it is very clear that for small change in emitter base voltage, the change in current is large. Okay, so that's why the input resistance will be quite low. Okay, now another thing that we have to know from the characteristics curve is that as the collector base voltage increases from one value to another value, we can say that the conduction is getting more better. Why? Because large collector base voltage cause depletion layer at the collector base junction penetrate deep into the base, which reduces the resistance between emitter base and collector base region. Okay, so as the value increases from 0 volt, then 1 volt to 6 volt, the conduction is more better. Now another point is that this particular point, okay, and this particular voltage, it is the cut-in voltage or threshold voltage, that is below which the emitter current is very small. Okay, this is because substantial emitter current will flow only when emitter base junction is forward biased beyond knee voltage, and that particular voltage is 0.7 volt for silicon and 0.3 volt for germanium. Okay, so this curve is plotted for silicon, that is at only from 0.7 volt there will be a substantial increase in the emitter current for a small change in the emitter base voltage. Okay, so that's about the input characteristics for common base configuration. So next we move on to the output characteristics for common base configuration. So output characteristics curve is drawn between the VCB, that is collector base voltage, and collector current for a given value of emitter current. Okay, so here shown the collector base voltage in volts, then collector current in milliampere, then emitter current also in milliampere. So in order to plot this particular curve, first we keep the emitter current in a constant value, then for the different values of collector base voltage we note the values of collector current and then plot the particular output characteristics. Okay, now in the output characteristics for common base configuration, we have to note three regions, that is active region, saturation region and cutoff region. Okay, so first one, that is the active region. So in this region, for various values of collector base voltage, or as collector base voltage increases, the collector current is almost equal to emitter current. Okay, first point is that as collector base voltage increases, collector current is almost equal to emitter current, and the change in collector current is very small, or we can say that almost the collector current is constant in this particular region. Okay, now regarding the values, consider this case, that is emitter current is some -1 milliampere, then as VCB increases, the collector current is almost constant and it is having a slight less value than the emitter current. Okay, that is in active region IC is slightly less than the emitter current but almost equal to emitter current. Okay, and actually the transistor is normally operated in this active region. So although the collector current is practically independent of the collector base voltage over the transistor operating region, if VCB is increased beyond a certain limit, then what happens is that IC, that is collector current, increases rapidly, and this is due to the avalanche or Zener effect, and this particular condition is known as punch through or reach through. Okay, that is noted over here, that is as the breakdown, and actually in this condition, when it occurs, large current can flow. Possibly it destroys the device too. Okay, that is, if we increase the collector base voltage beyond a particular limit, then there will be a rapid increase in the collector current and it may destroy the device. Now another important thing from this active region is that, similar to that of the input characteristics, from this region we can find out the output resistance. Okay, the output resistance can be find out from this region. So the output resistance, it is the ratio of voltage and current. Resistance means it is ratio of voltage and current, that is a change in collector base voltage to change in collector current for a constant value of emitter current. Keeping emitter current constant, the ratio of change in collector base voltage to collector current gives the output resistance. Okay, now what will be the nature of the output resistance? Whether it will be low or high, the output resistance will be high. Why? Because as a large change in collector base voltage, or for large change in collector base voltage, the collector current is almost constant, or there is only a small change in collector current. Okay, that is, for large change in collector base voltage we have small change in collector current, so the output resistance will be high. Okay, so that's about the active region. Second one, we have the cutoff region. Okay, so in cutoff region, the thing is that even when the emitter current is 0, there will be a small collector current, and that particular collector current is the leakage current. Okay, so that's about the cutoff region. And next, that is the saturation region. Okay, so in saturation region, the collector current IC flows even when the VCB is approximately 0. That is, even when VCB is 0, we have some collector current. Okay, now even when the externally applied bias voltage is reduced to 0, there is still a barrier potential existing at the collector base junction. Okay, actually this is the reason why there is some collector current even when the VCB is 0. Okay, now beyond that, when VCB is decreased to some -1 value, then that particular current will also be in a decreasing manner. Okay, so that's why here we get a slope in the curve, that is in the saturation region, that is there will be some collector current when VCB is equal to 0, and that particular value drops to 0 when we increase the collector base voltage to some negative values. Okay, so that's the three regions in the output characteristics, and this is the explanation for output characteristics for common base configuration. So thanks for watching the video. For watching more videos, please subscribe our channel Jnana Learning.